So let me introduce Mr. Suhail Basalama. Mr. Suhail is a PhD candidate from UCLA, and he's a student of Professor Jason Cong. If anyone still remembers, Jason is my academia idol, the only academia idol, the greatest academia idol. And if you still remember the family tree, I introduced that in the first lecture. This is me, and this is Professor Deming Chen, and this is Professor Jiru Zhang, and then that is Professor Jason Kong. So he's my supervisor's supervisor. So technically, Suhail, you are one generation above me. So if I look at, I see, I have to bow to you. So
No, no, not really.
you're one generation
Thank
earlier.
you.
You're above my hierarchy, one level higher hierarchy. um,
Thanks.
and this is the first guest lecture in the entire series. And after Suhail, we're going to have guest speakers from Professor Deming's group, from Professor Jiru's group, all about the recent, the most advanced HLS research in this area. So if you look at it, all of these greatest professors and the greatest, smartest students are still working in this area. So it's still with a lot of interest, and industry are also interested in this. Okay, so that's all from me. I guess, Suhail, you can start your lecture. And thank you again.
Thank you so much for the introduction, and thank you for inviting me. It's my honor to present in your class. Yeah, as Professor Howe said, I'm a sixth-year PhD candidate at UCLA, graduating soon. And today I'm going to talk about data flow accelerators for DNNs using high-level synthesis. And feel free to ask any questions either during the lecture or after. So let's get started. Okay, today I'm gonna talk about, I'll give a brief introduction about context of this work and research. And I'm gonna start with the FlexCNN framework. This is my earlier PhD work. It's an end-to-end framework for composing CNN accelerators on FPGAs. And then I will talk about Stream-HLS, which is my recent work called Stream-HLS towards automatic data flow acceleration. And so first, I want to talk about traditional computing and the challenges we are facing. So as we know that Moore's law has been slowing down to reaching the physical limits of silicon substrate, to general purpose computers like CPUs and GPUs usually sacrifice efficiency for being general and flexible enough to run any algorithm. And we can see that with customization, like we can gain like orders of magnitude improvements in efficiency in terms of performance and power when we go from CPUs to CPUs and GPUs to general purpose DSPs and into dedicated silicon. And the rise of compute and memory hungry AI algorithms made this matter worse. So this led to the rise of custom and domain-specific hardware on ASIC and FPGAs. For example, as you know, Google have their own TPUs, tensor processing units, built as an ASIC device. Cerebras are wafer scale accelerators. And then Microsoft used FPGAs for their data center workloads called the Microsoft Brainwave project. So, and I want to talk about this idea of generality versus specialization. So we know that general purpose CPUs can run any algorithm. They are like Turing complete. And the semantics of the algorithm are usually fully embedded in the software. And they are the most flexible, but also the least efficient. They waste a lot of power and energy, and they have low performance compared to specialized accelerators. On the other hand, fully specialized accelerators can run only a single algorithm usually, and the semantics are fully embedded in the hardware of the algorithm that you are accelerating. And they're also the least flexible, but also most efficient. But as we know in the real world and the research, there's a spectrum between these two extremes, where part of the algorithmic semantics are in hardware and part are in software. And so with this context, we have the idea of a scope, or where the scope of a hardware architecture is the set of algorithms or workloads that it can execute. So if we look at this graph, for example, CPUs and GPUs are general purpose, so they run basically any DNN. FlexCNN, first work I'm talking about, can, for example, run a family of ResNets, ResNet 18, ResNet 50, etc. But it requires some software runtime instructions to control this data flow architecture. And then on the other extreme, we have Stream-HLS, which I'll talk in the second part of the lecture. And this one is fully customized for a single DNN or workload. We have also another work, Phoenix, which is in progress, but I may not talk about it today because it's still work in progress. So, and then there is also in terms of the architecture, the hardware architecture itself. You know, the CPUs and GPUs are based on the von Neumann architecture. And what this is basically a load, compute, store architecture. And the execution model is basically execution, sequential execution of instructions. While in data flow architectures, the different units are executing in parallel, and the execution is based on the data availability. And in terms of memory, the von Neumann architectures have shared memory for instructions and data, but for data flow architectures, they are usually data dependencies will dictate the computation. And for the control flow, we have the program counters in the traditional von Neumann architectures, which will direct the execution flow. For data flow architectures, execution will be triggered by data availability and readiness. And for concurrency, you know, we have to design all these out of order processors or the massive parallelism in GPUs to allow this parallelism, and we need to describe it explicitly for von Neumann architectures, but for data flow architectures, concurrency is natural, basically. And this is an example architecture diagram, and this is an example of the architecture we do in Stream-HLS, for example. So let's start with the FlexCNN, which I call it a hybrid von Neumann data flow approach. So there are multiple challenges for accelerating CNNs and DNNs in general. First one is the computation to communication ratio disparity between CNN layers of the same type. Excuse me. And then the second challenge is handling various types of CNN layers. For example, there are special convolution layers like transpose and dialectic convolution layers that are not easily supported in hardware. And then there's also the end-to-end integration with machine learning frameworks. So FlexCNN data flow architecture basically looks something like this, where it's a data flow architecture made of hardware components that perform specific tasks like this for diff convolution, for ReLU activation, for the normal standard convolution, etc. And it reads the data from off-chip memory. This is like the load in the von Neumann architecture, and writes the data back to memory. But it doesn't process each layer by itself, but it can process a block or a subgraph of a CNN model, for example, and that's why it's kind of hybrid in between. And it's basically also streaming data flow architecture. The main compute engine is a systolic array architecture. I'll not go into details about this, but basically systolic arrays are a 2D grid of processing elements that allow forwarding of data between processing elements for data reuse, and this saves a lot of time and energy. And then for other modules, it's a sliding window. This is a common architecture for stencil kernels. So the computation to communication disparity within CNN layers of the same type, what I mean by this is, so, you know, like for a given algorithm, you have specific problem sizes, like the number of input feature maps, the output feature maps, the kernel size, and depending on the specific like parameters of the convolution, for example, it can have a different ratio between the amount of computation that we are doing and the amount of data that we need to move between off-chip memory, for example, and the accelerator. And this is like needs to be handled differently. For example, communication. I see a question.
Oh, no. I'm just saying that if they don't want to disturb you, they can type their question. But since we're already here, if you do have questions, feel free to unmute yourself and ask. Just
sure.
Just interrupt our speaker. He won't be offended.
Yeah.
Thank you.
So I was saying that, for example, if a layer is communication bound, that means we need to focus more on optimizing data reuse, on-chip buffers, the off-chip bandwidth. And this is actually has been the trend for transformer models. They are communication bound and they are not bottlenecked by the amount of compute units, but rather by the off-chip communication, by the data movement, etc. And then on the other hand, we have the computation-bound layers, and these will require, they are not bound by the off-chip bandwidth or the amount of on-chip memory, but rather by the amount of compute engines, basically, or ALUs or processing elements that are available to do this massive parallelism. So within CNNs, like multiple CNNs will start with a shallow number of feature maps, but a wide height and width of the feature maps, and then they slowly narrow down, and this causes a disparity, and that's what we mean here by the disparity of computation to communication ratios. And the solution to this we propose is dynamic tiling. So when we do tiling, this can change this ratio, and this can help in the data layout of the transferring the data between the accelerator and the off-chip memory. So for example, if we choose a set of tiling factors for some convolutional layer, we can see that we may take more time loading the data from off-chip memory, while the weights do not take that much time, and then the actual computation takes this time. But if we choose another set of tiling factors, we may be able to better balance this execution pipeline.
There's a question,
I see a
question in the chat. Yeah, good question.
So, yeah.
Can you repeat the question?
Yeah. So the question said, is dynamic tiling done during runtime or during synthesis? Actually, it's done during runtime. So it's given as instructions during the hardware execution, like CPU instructions to, for example, determine the size of data that we are loading and operating on. So these are runtime parameters. Yeah. So the next, okay, and here is a demonstration. So we did this experiment where we have uniform tiling factors for all the layers of a CNN that's denoted in red. And then we tried also with this dynamic tiling factors, and we can see that this can help improve the performance a lot, from around 24 gigaflops to around 149. And you see that we are able to improve the computation to communication ratio for this open pose CNN. Any questions so far?
I have a quite general question. I think the dynamic tiling is pretty cool. What's the challenge of doing so? Do you see any difficult points?
So by default, usually people would use fixed tiling factors in HLS, but if we want to use, and this will give you like deterministic performance results, HLS reports and all that. But once we use this dynamic tiling factors, you need to pass the specific tiling factors as arguments to each hardware module. and this will prevent like the actual HLS report results from showing up. So we usually need to do either co-simulation or RTL simulation, or actually run it on hardware. But HLS still will be able to do all other optimizations like pipelining, enrolling. But for example, we cannot unroll the dynamic tiling factor. We need to unroll it by a constant factor, basically.
Got it.
Yeah.
Thank you.
Yeah.
As a personal advertisement, and you also know, the Lightning Sim. Do you think Lightning Sim can be useful here to examine the performance?
Yeah, I think Lightning Sim, since it's based on the RTL simulation, I think it'll be useful in this case. I haven't tested it because that was
yeah, of course.
Yeah.
I mean, just out of curiosity, you mentioned you have to run CoSim or execute on board. I personally think Lightning Sim could solve the problem.
Yeah.
There's another question.
Yep.
No, I mean in the chat box.
Yeah. So, and it said, how do you determine the tiling factors at runtime? And what parameters does it depend upon? I will discuss this later in we have like a design space exploration to search for these dynamic tiling factors, and then we will generate the instructions for each basically block of like subgraph of a CNN. And then
Yep, another question.
So what we mean by communication, so this question asks, could you shortly explain what exactly do you mean by computation to communication ratio on the actual hardware? Where is the delay coming from? Okay, so this notion of computation to communication ratio is basically for many linear algebra kernels or algorithms like convolution or matrix multiplication. You can calculate like how much data that this algorithm will require moving from off-chip memory like DRAM into the hardware. For example, for matrix multiplication, we have the matrix A I times K. This is the minimum amount of data that you need to transfer from off-chip memory to the accelerator. And then for B, it'll be K times J. And then for the matrix C, if you need to read it, it'll be I times J, like the sizes of these matrices. And then the number of operations will be that like the algorithm is based on the multiply accumulate operation. And this operation, how many times this algorithm will take will be I times J times K. And then the ratio between these two numbers will give you like how much volume of data that you need to transfer from off-chip memory and how much computations are there. And this is the ratio. But then, for example, if you don't have enough storage on chip to load the whole matrices, then you can read the matrix from off-chip memory multiple times, and this will change the amount of data that you transfer from off-chip memory to the accelerator. I think if you want to learn more about this, you can refer to the roofline model. It's a famous profiling like approach to see if an algorithm is communication bound or computation bound, and it doesn't strictly depend on the algorithm itself, but more on the level of data reuse that you choose. For example, if you choose to transfer all the matrices of your algorithm once, then this will require the most amount of on-chip memory. But if you have enough off-chip bandwidth, then you can like transfer the matrices multiple times from off-chip memory to the accelerator without needing so much on-chip memory. So it depends on the specific kind of scheduling or level of data reuse that you employ in your algorithm. Any other questions? Okay, so The second challenge we faced in FlexCNN is handling various types of CNN layers. What I mean by this is, so the communication to communication, the communication to computation ratio is for layers of the same type. For example, the normal convolution layers, they may have these different ratios. But here we are talking about layers of different types. For example, this ENET model, it's a small segmentation CNN network. It's made of 209 layers, including 78 normal standard convolution layers, 8 dilated convolution layers, and 3 transposed convolution layers. And I will discuss what these are in the next slides. So, but we see that we have various types of layers. And modern CNNs contain all like various layer types. So as I mentioned earlier, this compute intensive layers, normal, transposed, and dilated convolution layers. And then there are non-compute intensive layers like pooling, upsampling, activation, and batch normalization. All these are just bounded basically by the amount of bandwidth and on-chip memory that you have. So our solution is we use a versatile systolic array for compute intensive layers because it offers massive parallelism. And we use dedicated hardware for non-compute intensive layers. And this is the architecture I showed earlier, but more with how the architecture itself is with the DRAM input and output and the type of modules that we have. And the main compute engine is this versatile systolic array. Versatile systolic array because we are able to, it is able to perform both the normal standard convolution, the transposed convolution, and the dilated convolution. I will explain what these are types in the next slide. But basically, we are able to have this systolic array that is also dynamically configurable to operate on these layers efficiently. So transposed convolution, also known as fractionally strided convolution, it's an upsampling layer, but normal upsampling doesn't need any weights, but transposed convolution uses trained weights to produce high resolution feature maps. And it's used in these segmentation CNNs. And the naive algorithm of transposed convolution, we can implement it just like the normal convolution by inserting zeros in the input feature maps. For example, if the original feature map is 0, 0, 0, 1, 2, and 0, 3, 4, then if we insert zeros between each row and column, and we take this trained weights that we use for transposed convolution, then the transposed convolution operation will do the normal convolution on this feature maps, starting by this position, the next one, and so on. And then we will get this output feature map. So you see that the input was like a 2 by 2, like without the zeros, it was just a 2 by 2 feature map. And then we produced a 4 by 4 feature map. So this is like an upsampling process. But if we try to implement it like this naively in hardware, then this will result in a lot of zero MAC operations. And this is really bad for hardware because we will waste a lot of multiplication with zero operations that could be done in other things. Okay, I see a question. Okay, so this question is a good question. It said, for the compute intensive and non-compute intensive layers you mentioned, is it similar to dense matrix multiplication versus sparse matrix problem? So it's actually related, but kind of orthogonal. So sparse matrix multiplication for sure is communication bound because of all because of this specific ratio, but it will not be a fixed value compared to calculating it for dense matrix multiplication. But also, for example, matrix multiplication is computationally bound in general, while the matrix vector multiplication is communication bound. because it's bound by the matrix that we are multiplying. Basically, like matrix multiplication, we have 3 computational loops that operate on 2D tensors. So it's 1 degree higher. That makes it kind of computation bound, while the matrix vector multiplication is just 2 loops, and the largest rank of the tensors is also 2D. So that makes it more communication bound. And for sparse matrix, since a lot of the values in the matrix are zeros, then that reduces the actual size by a lot, and it becomes communication bound.
I just want to quickly jump in here. I think this is indeed a question that we can talk about in a lot more detail, but just to be brief, I like what Suhail has just said. It's orthogonal. But especially I want to comment on the sparse matrix problem. Depending on the sparsity level, it can be compute bound or it can be communication bound. And depending on how you store the sparse matrix,
that's true.
It can also change. Say if you just store the sparse matrix in the original format, then you keep transferring all those zeros. But you skip them when you compute. That can be a different story. But if you store the sparse matrix in a very smart way and you transfer only the non-zero elements that could be compute bound because you just send very few data, but then you have to decode it, right? So the sparse matrix problem is actually very interesting and intriguing. It's hard to say whether it's compute or non-compute. It's all based on how you want to store the matrix and how you want to represent it, how you want to encode it, and exactly how sparse it is.
And that's the sparse matrix multiplication. For example, actually, Ling Hao is also a student in our lab, and he has a lot of works on this. He is now a professor at Yale, but he has done a lot of work on the sparse matrix and matrix vector multiplications. But also you have like very sparse workloads, which is like only 0.01% actual computations, and you have something like 50% sparse. So there's this like spectrum, as Professor Hao just mentioned.
Yep, this is a very timely question.
And similarly, the dilated convolution, also called Atrau's convolution, maintains the resolution and coverage of feature maps by expanding the receptive field of the convolution filters by inserting these zeros in the filter or kernels of convolution instead of the feature maps. So for example, if we have this 2x2 filter, and now we can do the normal convolution operation, the filter itself covers like a 3x3 window instead of a 2x2. And it's also used in segmentation and medical imaging. This also results in a lot of zero multiplication operations, and it's not good for hardware. So the original systolic array that we have designed just for normal convolution can perform these operations, but now will result in huge underutilization of the hardware resources. And the number of zeros we insert here and here, here it's called the dilation rate, and here it's called the stride for the transpose convolution. And we will show that an efficient implementation of transpose convolution can be also done with normal convolution through a decomposition approach. So if we have this original, the feature map with zeros inserted, you can notice that there is a pattern. If we take this inverse filter and we apply it here, only the 4 corners are needed for this computation, right? And then if we slide it 1 to the right, like just the next iteration, then we will need only the 8 and 2, the top and bottom. And if we move it 1 step further, then we are back to the 4 corners. And if we go to this position, then we need the left and right. And then if we are in this position, then we only need the middle, the one in the middle row. So with this, so that's why I do this coloring. And now if we take this dense input feature map, we can basically do the normal convolution using these dense, smaller filters. And once we get we do normal convolution, but with different shapes. For example, here we will do 2x2 filter. Here we will do 1x2, and here 2x1, and here just a pointwise convolution. And this results in the same output feature map, but without requiring all these zero operations. And the ideal speed up with this approach is calculated with this formula, which is the stride squared of this transpose convolution, if we remove all these zeros. And similarly, for dialectic convolution, exactly the same approach. If we look at the positions where the filter will be positioned, now we can decompose the feature map itself into these dense feature maps, and then we only use the dense filter to compute the values, and we get the same result. And this is the formula used to calculate the ideal speedup. And this approach, so we could have implemented 3 separate accelerators, but the problem with this approach is we want to maximize the reuse of hardware reuse. But if we did it in this way, where we have 3 different systolic arrays for each type of convolution, then when we are operating on normal convolution, we will only be using this part of the FPGA or hardware resources, while the other ones will be idle. So ideally, we would like to have them all operating using all the hardware resources, and they can be dynamically configured to implement these 3 approaches. And that's what we did. We implemented this versatile systolic array that is runtime configurable depending on the specific type of convolution. And our approach shows close to ideal speedups, the one we just calculated with these formulas, except for communication bound layers. So the purple lines are the ideal speedups. The purple lines are the ideal speedups, and the yellow lines are the ones we actually achieved. And we noticed that this implementation with the versatile systolic array is achieved by modifying the systolic array to support these 3 types of layers, but it comes almost at free cost, only with a modest area resource overhead. Here it's like 45% DSP compared to the original standard systolic array that consumed 42%, 3% increase in flip-flops, and 7% in LUT lookup tables. And for the on-chip memory utilization, it's kind of mixed, because here, like, this depends on the HLS, on whether it chooses BRAM or URAM for using, like whether it allocates URAMs or BRAMs for the specific buffers in HLS. And lastly, the challenge 3, the end-to-end integration. So a lot of previous works were focusing just on the accelerator itself and not considering the rest of the pipeline overhead, which is like when deployed in the real world, you need to take care of all the steps from the of the inference, including the other image processing pipelines and everything. So a typical CNN pipeline will involve pre-processing the inference, the actual CNN inference, and then the post-processing. And we propose 2-level pipelining approach. The first one is we are pipelining at the software level, where the pre-processing CPU is happening, and then the FPGA inference, and then the post-processing, and then we pipeline these stages. And then we also do the hardware level pipelining, where we are overlapping the DRAM reads with the kernel invocation and the DRAM writes. And this results in 2x speedups and then 5x with the second pipelining. So someone earlier asked about how we decide the tiling factors, and all these things. So here is an overview of the framework. So we take an Onyx model or a CNN model, and we give it the architecture template that the types of layers that will be in this CNN. And we will start by CNN layer mapping. This is not done fully automatically, but basically we will break the network into smaller parts. Each part will run at a single invocation of the accelerator. And then, given these parts, we will do a design space exploration that will search, like we have an estimation performance model that will give us the estimated latency under a specific set of tiling factors. And we use a greedy search algorithm to basically start by exploring the different possible tiling factors for each chunk of this CNN. And once we get the best tiling factors based on this estimation model, then we will generate the instructions that will control the hardware during runtime. And then this design space exploration will also explore the different hardware parameters that will be used. For example, the size of the systolic array, the number of columns, the sizes of the number of rows, the sizes of on-chip memories, etc. And we generate the hardware, and then we have the runtime instructions for a specific CNN. So I've already discussed this. Yeah, so the design space exploration actually performs two steps. One is exhaustive search of the hardware parameters that can fit on the. So the performance model we have estimates both resource utilization given some specific parameters, and also it estimates the latency of a given set of tiling factors. And for that, we use the greedy search to find these dynamic tiling factors for each group of layers. And here are more results on the transpose and dilate convolution. We can see that these small layers are communication bound, and we don't achieve the ideal speedups. But once we move towards larger layers, we are close to the ideal speedups expected by eliminating all the zeros. And yeah, and then we did more evaluation results on CPUs, GPUs, and other FPGA works. Initially, OpenPose, that was the original network we targeted, and we used float 32 bits, and we showed that our latency and throughput are comparable to a Tesla V100 GPU. And for UNet, we compared it with other works that implemented UNet, and we showed that we have close or better speedups. For example, this work was using fixed 16-bit, but our data type is float 32-bit, and we are still better than this work. This work actually uses even smaller data types, which allows better parallelism, and it achieves better results than us. And I see a question here. Is greedy search better for finding the tiling? Okay, the question is greedy search better for finding the tiling factor compared to other kinds of search? So not necessarily. So this greedy search may not be optimal, but if you try to explore all possible tiling factors for all the layers, the design space explodes. It's a combinatorics explosion for if we try to find all search the whole design space. So we just chose the greedy search because it was feasible and scalable at runtime. We also compared with the Vitis AI DPUs. These are hard, like RTL manually optimized designs, IP blocks that are used to accelerate specific CNNs. And we see that our implementation is actually comparable to these works in terms of the latency, especially for this medium size accelerator. Yeah, go ahead.
Yes, my question is that when you use the floating point 32 bits here, does it cause very high resource usage? Usually the floating point is not hardware friendly, is it correct?
Yeah, so floating point usually uses much more resources compared to int or fixed point on FPGA, even for the same bit width. For example, I think for a multiply accumulate floating point 32, it uses like 5 DSPs per MAC, while for int, I think it uses a single DSP or maybe two. Similarly, even for like lower bit widths, it even uses less. Like you can pack, I think, 2 MAC units in a single DSP or something like that. So yeah, it was
But
hard
in this,
to have an apple-to-apple comparison.
okay. But in this case, you can still fit all of the requirements into the hardware, is it correct? I mean, you can still fit all of the floating point conversions here in the FPGA.
Yeah. So like if you have floating point 32-bit, you may not be able to have a very large systolic array. So it'll be a small or medium-sized systolic array. But maybe if you have 8-bit type, then you can increase the size of this systolic array and increase the parallelism.
That makes sense. Thank you.
Yeah, you're welcome. So this was the FlexCNN work. And now I'm gonna, yeah,
One second. We may need to speed up a little bit.
yeah,
So
yeah,
we
yeah,
have less than half an hour and we need 5 minutes for the quiz.
sure,
Yeah, so actually,
sure.
I'm just sorry, go ahead. Just a quick reminder.
Yeah. So Stream-HLS, this is our latest work that was at FPGA 25, and it's a pure data flow approach. So there are two key factors limiting wider adoption of data flow accelerators. One is the difficulty of automating hardware design, and that is like how to automatically implement a given known design point or a schedule. And then the other one is the complexity of exploring this huge design space. And this is basically how to find a good design space and design point in this huge design space. And many prior works have tackled these challenges, but significant issues remain unresolved. So just an overview of prior HLS automation works. There have been a lot of works on pragma insertion for HLS, automatic pragma insertion. So you are given some plain C++ code, and these frameworks will try to insert the pragmas that will optimize the performance. But they do not explore like code and loop transformation opportunities. They just explore the different combination of pragmas that you can put in this HLS code. And this limits the possible optimizations that you can do. Other works, they target single kernel frameworks like O2SA and SODA. And by this, for example, it means just a single convolutional layer or a matrix multiplication kernel. So they don't take multiple like a CNN or an actual like multi-kernel application. And it performed code transformation and design space exploration. But as I mentioned, they only support single kernel application. There are abstraction frameworks like Allo and HeteroCL. These works, they decouple algorithms from hardware scheduling optimizations, which is really useful, but they still require manual design space exploration. And lastly, there are multi-kernel frameworks like Scale-HLS, HIDA, and POM. These works, they perform both code transformation and design space exploration for multi-kernel applications. But all these prior works lack streaming data flow capabilities and have limited design space exploration. So Stream-HLS.
Just a quick comment for the students. We are going to have guest lectures talk about Allo and Scale HLS and HIDA. So just to remember that this is about Stream-HLS, and we're gonna learn what Allo and Scale HLS and HIDA are exactly about. Well,
Yeah.
next time I'm gonna swap the order. But yeah, just a quick comment. Please go ahead.
Okay. So Stream-HLS falls under this last category, but it produces globally optimized data flow designs with streaming capabilities and uses mathematical programming for design space exploration. And there's the overview of the framework. It takes a PyTorch or C++ code and does a lot of MLIR passes to do the optimization and design space exploration, which I will explain shortly. So here is an example of a motivation example. So we have this kernel called 3MM. It's basically 3 matrix multiplications where the first 2 are input to the third one. And this is the data flow graph of the algorithm. And this is the example code snippet. And this is what Stream-HLS will generate. And all of them will be operating in parallel, and the data will be forwarded based on the availability of data, but they are all executing concurrently. So for such multi-kernel applications, we identified 3 critical but often conflicting optimizations that will determine the overall performance. First one is node-level pipelining. Second one, graph-level pipelining, and third one is node-level parallelization. So for node-level pipelining, in HLS, if you put Pragma HLS pipeline for this code, we see that the innermost loop is this reduction loop. So there is a loop carry dependency, and we will not be able to achieve II1 because of this loop carry dependency. But and this will give us an estimated performance of around 1 million cycles. But to avoid this short loop carry dependency, we can do a loop permutation. We put this reduction loop outermost, and now the consecutive iterations will not operate on the same data cell, and we will be able to achieve an initiation interval of 1. This gives us around 4x speedup. However, this same loop permutation interchange can impact the degree of concurrency if we have now multiple kernels that depend on each other. So for example, in this code, even though we have II4, we know that this temp1 will be ready after only around 127 iterations of this innermost loop. Because the reduction loop is the innermost loop, it will be ready after only 127 iterations. On the other hand, if we permute the k to the outermost, now the first cell of temp1 will be ready after around 260,000 iterations. So this is a massive difference, even though this achieves better II. I think there's a question. Can you explain the loop carry dependency and the reduction loop? Why can't II be 1? Okay, sure. So in this code on the left, we have K, the reduction loop, and we will be reading and writing to the same cell in consecutive iterations. So at iteration 0, so there is this, so if we draw the pipeline, we will load temp 00, for example, and then we do the operation, and then we need to write temp 00. But this latency is pretty long, and the next iteration needs to wait. So there is a conflict in the possible pipeline, and the minimum latency that we need to wait for the next iteration will be 4 cycles, and that's why we achieve II4. But in this case, we will read from cell 00, and then we write to cell 00, but the next iteration is actually not reading from 00, but reading from 01, because we have now I and J are innermost. Does that make sense?
I think the multiplication is not necessarily 4 cycles. I think it can be 1 cycle, but the major bottleneck is the read and write.
Yeah, the read and write to memory, because like on the left, we are reading and writing from the same memory cell, and it takes a few cycles to commit. So the next iteration cannot start. But on the code on the right, we are writing to different memory cells, so they can perfectly overlap.
Okay, I guess we can proceed.
Okay, so that this difference indicates that temp1 must wait until the next node that will consume temp1 must wait until we finish all these iterations. So here's a illustration of what's going to happen in different loop permutation scenarios. So in the first case, temp gem3 will have to wait until the end of execution of both gem1 and gem2. And this sequential execution is due to the choice of loop permutation or the use of shared buffers. We are not using FIFOs to forward the data. Here, we have a better solution using some set of loop permutations and streaming FIFOs, but it's not the best overlap that we can achieve. And in this case, we have under a certain set of loop permutations, we achieve the maximal overlap execution with the best loop permutations. And the design space in this case, if we are trying to explore for 3 matrix multiplications, will be the multiplication of, for first loop, we will have 3 factorial loop permutations times the second loop times the third loop. This gives us 216 different schedules. And I think this will be the time for the quiz.
Yep, I will launch the quiz. All right, so students, if you are not able to see it, please let me know. The quiz should be ready for you to answer. I think it either pops up or you can find it under the polls and quiz. You can see it.
Yeah.
Okay, good. We will pause here for 4 to 5 minutes. We will resume at around 4:31. Well, I guess if you have questions, you can ask.
Yeah.
If you have questions regarding the quiz or the previous slides, you have questions, you feel free to ask.
Some student asked, will it be automatically submitted when the time is done?
I think so. I'm seeing a lot of students are submitting their solutions. I see right now we have 65%, 48 students already submitted. I think you can just keep submitting as long as I don't end the poll. All right, we have 1 minute left, and we are still missing 7 answers. Now 6 answers. 6 of you haven't submitted yet. If you really have troubles submitting the answer, you can take a screenshot or whatever way you can to prove to me that you're listening. I'm all good. Say you can take a screenshot, you can take a selfie, you can do whatever you can to show me that you're actually in the lecture. Okay, don't worry. So if you really have trouble, you just do whatever you can. Like I said, take a selfie, do whatever you can to show that you're attending this lecture. That's all good. Don't worry too much. Shoot me an email later. We have 15 seconds left. 15 seconds. All right. 4, 3, 2, 1. There we go. And pull. Okay. Interesting. I'm sharing the result. Okay, can you? Okay, you all can see the result.
Yeah. Most
Okay.
got it right.
Yeah, most we got it right. I will stop sharing. Oh, but don't worry about it. You answering the question wrong will not necessarily reflect in the score. So don't worry about it. It's just okay. I will stop sharing, and you can continue.
And just to explain, so if we look at the previous code here, how many possible permutations for the first one, for example, it's 3 factorial. And if we, for each possible like permutation, we can also permute this 3 factorial. And then for each of these 2, we can also permute 3 factorial. So we will have 3 factorial times 3 factorial times 3 factorial. And for the example we gave was like 6 loops, 2 loops, 3 loops. So it'll be the 2 factorial times 4 factorials times 6 factorial times 3 factorial or something like that. So yeah, this the design space quickly explodes, especially when you increase the number of kernels and the number of loops. And the next optimization is the node level parallelization. So far we've just talked about the loop permutation, but also in HLS, we do like loop unrolling to maximize parallelism within each loop nest. So, but how to choose good tiling or parallelization factors? So let's say we have these 3 kernels with different number of operations. For example, the first one has 2 million, the second one 4 million, the third one 3 million. If we use like some prior approaches, we'll just use uniform parallelization factors for all the kernels. And this will, for example, parallelization factor 2, meaning we cut the time by half for each one, for example. We get this type of execution graph. But a better tiling factor would be, we call it adaptive parallelization, meaning we allocate parallelization or computation resources proportional to the number of operations of each node. And in this case, we use 2, 4, and 3. We see that the amount of the latency of each computation is balanced now, but we still are not doing the best loop permutation. So it's orthogonal to this parallelization. And then Stream-HLS, what we do is we combine both the adaptive parallelization with the loop permutation that will maximize the concurrency and parallelization within each node. And the tiling and parallelization design space using only divisor tiling factors. And this example is around 331,000 design points multiplied by the previous design space, which is 207, 216 or something. This will give us total design space of 71 million possible schedules and different optimizations. So given only these three optimizations, we have three challenges. One is how to automate streaming capabilities with FIFOs once we know a specific design point. And two, how to estimate the performance of a Dataflow design point with a mixture of shared buffer and FIFO communication, and how to search this huge design space. So for streaming automation, to legally replace a shared buffer between these two nodes, for example, temp1 or temp2 that was used for communication between two matrix multiplication kernels, two conditions must be met. One is the number of writes to that buffer needs to match the number of reads. And the second condition is the order of writes needs to match the order of reads because we are using a first in, first out channels. So the following these two passes that we implemented in MLIR automate this process and replaces shared buffers with FIFOs whenever possible. And here's an example. So first, we legalize shared buffers into single producer, single consumer relationship through buffer duplication. So by this, I mean, you see that, for example, in the code here, C is read 32 times 32 times 32 times and written to the same amount of times. But here it's read only 32 times 32 times. And also we have two reads and a single write. So the question, these large space numbers are significant because the tool must theoretically search the entire space to find the optimal flow. Is that correct? Yeah. So we may not be able to explore the whole design space, so I will show in the next slides how we search this design space. One approach is we search the whole design space, but it may not be scalable. The other one, we can reduce the size of the design space through multiple techniques, which I'll just explain in a minute. So in this case, we see that we have two reads and two writes, and the number of writes is 32K, while the reads is just 1K reads. So condition one, the number of writes and reads does not match. But if we can convert it into this code where we have a local buffer that will be used for the local accumulation of data, and then we create shared buffers that will only store the final values. So here you see that K equals 32 means the last iteration of this loop, we will write the values from the local buffer into this shared buffer. Now we have to this shared buffer 2 only one read, one write, and the number of writes equals the number of reads. And now condition 1 is satisfied. There's another question. How can we effectively to prune the search space and focus on viable candidates? So most of these candidates are viable, and we don't, in this work, we didn't actually prune the design space, but there are like a whole literature on like exploring the design space and doing pruning and strategies and all that. But I will show in this our work one instance of how it's possible to not necessarily explore the whole design space, but also achieving good results, but maybe not the optimal ones. So it's like a trade-off between optimality and the scalability. So this was the first optimization. We achieved the condition 1 for FIFO, converting shared buffers to FIFOs. Now the second condition, if we look at this example, we are writing to this shared buffer in the order ij, but we are reading at the order ji. So the access relation for the write is different from the read access function. And so the order of writes does not match the order of reads. So in this example, they're not equal, so the shared buffer will be maintained, because if we replace it with a FIFO, the result will be incorrect. But fortunately, these access patterns can be equalized through loop permutation that we just mentioned earlier. So in this case, if we permute these two loops, now we have ij, and in this case, we have also ij, and now condition 1 holds. And now we can safely replace this shared buffer 2 with a FIFO channel. And this takes us to the next step, which is the code transformation and the design space exploration. So here is what I mean. Where this combined optimization is where we search the whole design space, and this other pipeline is where we divide it into 2 steps. We first search for the design space of the loop permutation separately, and then we search for the design space of the parallelization separately. And also for the design space exploration, to evaluate a new design point, if we like, some approaches will rely on the HLS tool to run the synthesis and see the performance results, but this will be very slow. In our case, we built a performance model that will estimate the performance under given parameters, and will also estimate the resource utilization. And we explore the design space using mixed integer nonlinear programming. Here is briefly how we explore, do the performance modeling. We model the application like a DNN as a directed acyclic graph, where a node is a perfect loop nest representing a high-level operation like matrix multiplication, for example, or convolution. And edges are the read after write or true or flow dependencies between the nodes. And then the DAG is sorted in a topological sort, and the closed form formula will be constructed based on this graph. And more details about the performance modeling is in the paper. And then for the mixed integer nonlinear programming DSE, since we have this closed form formula to estimate the latency and their specific schedule and their specific loop permutations and tiling factors, we can use this model as an objective, this mixed integer nonlinear program. And for the graph node level pipelining, which is affected by the loop permutation, we have d factorial binary variables per node. For node level parallelization, we have d integer variables per node. D is the depth of the loop nest. And this will find the best tiling and roll factors for each node. The d factorial binary variables will find the best loop permutations of each node. And then the combined optimization is the whole design space, where we have d factorial binary variables and d integer variables to find both best loop permutations and tiling factors all at once. But this will be the huge design space I showed earlier. So in our experiments, we tested on 7 polybench. It's a famous benchmark made of many linear algebra kernels, 2 multi-layer perceptrons, 2 transformer blocks, and 2 CNN blocks, and 2 synthetic kernels. Medium problem sizes to reduce RTL simulation times. We use RTL simulation time because for these data flow designs, HLS report may not be accurate. I will show in the next slide. And this is the setup. So Opt5 is the one where we explore the whole design space. Opt4 is where we find the best loop permutations first, like the 216 points in the example we showed, and then we explore the remaining 300,000 points for the tiling factors. So in this case, it's the multiplication of these 2 spaces. In Opt4, it's the addition of these 2 spaces. It may not be optimal, but it's usually close to optimal, which I will show in the next slides. And then here are the other optimization. For example, this one shared buffer to FIFOs only, like without changing the schedule, whenever like the conditions I mentioned are applicable. The second one is where we don't do parallelization, just optimizing the loop permutation. And then the opt3 is where we don't change loop permutations, we just optimize the tiling factors and unroll factors. And 4, as I mentioned, is the doing them in 2 separate steps, and 5 is where we do them all together. Here is like a validation of our performance model, just to make sure that it matches the actual RTL simulation. We see that our performance model is pretty accurate, actually in many cases more accurate than the VAST report. As I mentioned, VAST report may give you optimistic report about the performance of your data flow design, because I think it simply takes the maximum, like the longest latency stage of all your tasks, regardless of how they are connected, or if like how data flows between 2 tasks. Yeah, so for opt1, our HLS Stream-HLS model is around 99% accurate. For when we introduced parallelization, it's less accurate because our model, it's difficult to estimate the actual achievable II before running the HLS tools, and that's why we lose some accuracy. And then we compare to actually.
I want to quickly say that because we're the time is done. I mean, the end of the lecture. If you have to go, you can leave, and if you want to stay, you can stay.
Okay.
From now on, it's not mandatory. But Suhail, feel free to finish what you're presenting.
Yeah, almost done. So yeah, we showed a lot of improvements compared to manually optimized tools, the ones I mentioned earlier, where you can manually optimize the schedule of your design. And also we achieve big speedups compared to the prior automation approaches, basically due to the streaming capabilities of our designs, and also the design space exploration that considers the global scheduling of these circuits. And then here is going back to the 3mm example, motivational example. We showed that here is the actual like time traces of 3mm that we implemented compared to the prior works. And here is another one compared to another prior work. And we see that our work actually balances the latency of each node and also maximizes the overlap and concurrency between them. And here is an ablation study. This will show the impact of doing the optimization separately, like doing optimization, like splitting the design space. We see that in many cases, like the performance is almost the same as we do the combined optimization. And in some cases, combined optimization is actually better. But the scalability issue, if we try for the combined optimization, may not be able to solve for large problem sizes. So this is maybe the best other option. But of course, there are other pruning possibilities that we didn't consider in this work, but literature has a lot of these techniques to explore huge design spaces. And yeah, this is the conclusion. We showed that the slowdown of Moore's law and led to the rise of custom and domain-specific computing, and data flow designs have demonstrated effective performance compared to the challenges of AI in today's world. And yeah, we presented these 2 works, a hybrid point name and data flow architecture, and a pure data flow compiler for streaming Dataflow accelerators. Yeah, and feel free to explore these frameworks. They are open source at our lab's GitHub repo. Thank you.
Thank you so much, Suhail. This is really, really appreciated. I personally learned a lot. I've always been a big fan of this great work. This is great that I have the chance to listen to a live presentation. Thank you so much. And you actually talked a lot details that I wasn't able to cover in my lecture. For example, the systolic array, the roof-line model, and sparsity. I think you just gave me a great add-on. Thank you so much. And I appreciate everyone who stayed online and paid attention and asked all the questions and had this great discussion.
Sure.
All right. Thank you so much. I think we
You're
still have a
welcome.
couple. Yeah, I think
Yeah.
we still have some questions if you want to stay and
Sure.
address.
So one question, have you tried unified agentic environment for automatic DSE, one that includes all essential tools in sandbox and support parallel search? So, okay, at the time of Stream-HLS, like, are you talking about AI agents? If so, like, wasn't as popular, and also our modeling, since it was like deterministic and we have a good performance model, we didn't really need to use AI or machine learning algorithms for this purpose. And we just relied on mathematical solvers like Ample and Gurobi to explore this design space. At least it worked for the cases that we have, but it may not be as scalable. And here another one asks, do you think the main advantage of FPGAs for ML acceleration is the power efficiency, or is there a deeper compute advantage? Actually, there is a deeper compute advantage, as you mentioned. So FPGAs have like the flexibility that you can customize your circuit and highly optimize your accelerator and make it tailored exactly for the type of algorithm that you have. As I showed in the very first slides, that you have to sacrifice some flexibility for efficiency, and based on the scope of your accelerator and what you're trying to achieve, if it's a single CNN, then you can probably make it very highly customizable for that CNN application, and you will achieve massive speedups and power efficiency as well compared to GPUs or CPUs. And the advantage of FPGA compared to ASIC, this is also applied to ASIC, but for FPGA, since machine learning world is changing so fast, you can quickly design a new accelerator and deploy it using the same FPGA. But with ASIC, it's a long cycle and it may not be cost effective.
I also want to quickly comment on that.
Mm-hmm.
I personally think the advantage of FPGA is exactly of this data stream architecture, this data stream accelerators like Suhail introduced today. Other architectures like GPUs, CPUs, they are not good at this type of accelerator, especially for this streaming type of workload. That's why for starting from Suhail's guest lecture, the remaining of the whole semester, almost more than half of them are about streaming data flow and data streaming accelerators. So I think that's one of the main advantage of FPGAs.
Yeah.
Okay. All right. Okay. I guess there's no more questions, and I feel like everyone likes your presentations. They likes the work and likes your lecture. Really appreciate it.
Thank you for inviting me, and thank you for your time all. And thanks for the great questions, of course.
Thank you. Really appreciate it. Thank you so much. You have a great day, and let us know whenever you need our help.
Sure. Thank you so much.
Thank you. Bye, everyone. Bye-bye.